Welcome everyone to this course. In this lecture we will continue our discussions on the boosting algorithms. So last time we started from the idea of what bagging is, ensembles are, right, and we discussed the naive bagging methods where you combine classifiers. Then we also looked at the boosting methodology, and in bagging we looked at the random forest as a classifier, as an ensemble. We also looked at gradient boosted trees, GBMs, or gradient boosting in general. So as I mentioned in the previous class, the individual weak learners that are a part of the ensemble need not be of one type. Typically, it will be trees that will be used as constituent weak learners because they are easy to be learned. Okay, they are non-parametric methods and easy to be learned. That's why generally the gradient boosting methods like gradient boosting or even bagging, the constituent classifiers are taken to be decision trees, but theory does not stop you. You can have ensembles of neural networks, you can have ensembles of kernel machines and so on. Okay, there is nothing that stops you from taking different kinds of classifiers and doing an ensemble. So today we will continue that discussion on ensemble, and we will look at one very powerful algorithm called AdaBoost. Okay, remember in the definition of ensembles, especially in the boosting strategy, the idea is to iteratively keep adding one weak learner at a time. Okay, and when you add a weak learner, there is this alpha, which is the weight that is associated, that is given for the oat that is given by that particular classifier. Now in gradient boosting, we take this, treat it as a hyperparameter and keep it as a constant, right? But in the question is, in the most general formulation, we had an m here as well, and we can optimize over alpha as well. We can look at what the optimal step size is, or optimal weight that is to be multiplied with the weak learner, so that we get the best performance. So AdaBoost is one such algorithm, okay, where alpha is also learned in the gradient boosting way. As I mentioned the previous time, AdaBoost was an algorithm that was proposed, I think, in 95 or 96 as an ensemble technique, and it had very good performance. Now gradient boosting came later chronologically, and later people showed that AdaBoost is a special case of gradient boosting as well. So what I will do is, I will write down the algorithm of AdaBoost and just explain that as an algorithm, and then we will recover this algorithm via the gradient boosting that we did, okay, as a special case. That's what we will do now. Okay. Okay, so the AdaBoost algorithm. So let's start with a classification problem. Given a data set D, we have n samples, standard classification problem. Let us consider a binary classification problem, and let the labels be -1 and 1. Again, -1 and 1 because algebra works out nicely. Okay, so let us take them as -1 and 1. The AdaBoost algorithm is as follows. Initialize weights to data points. Uniformly. Let's call them WI M for the mth iteration. Sorry, this should be 1. Hold on. WI1 to be equal to 1 by n, for I is 1 through m. The subscript represents the data index, and superscript represents the iteration index. Okay, and we have m such classifiers that we are looking at. So now for m equal to 1 to m, do. The first step is to train a weak learner let's call it HM of x with the current weights on data, which is WIM. So please note that these weights they are not the parameter weights that we are talking about. These are the weights that we assign to data samples. You understand? The fundamental idea of AdaBoost is that you assign weights to each of the data sample, okay, and iteratively you keep changing the weights associated with each of the data sample. So remember that in any boosting algorithm or a ensemble technique, we will do a sampling with replacement. When we do sampling with replacement, so far we are treating all data points equal. But here in AdaBoost, we don't treat every data point equal. We change, we associate a weight with each of the data point, and that keeps iteratively changing as we move from one classifier to the other. Does it make sense? So that's the weight that I am talking about. So initially you give equal weights to all of them, okay, and then keep changing the weights associated with each of the data points. So that's what the idea is. So now I will give you a formula to update these weights as we move on. Okay. Now I am saying train a weak learner with the current weights on data. So what do I mean by that? So you will have to ensure that this is the distribution, okay, that is maintained on data points when you train a classifier. So how do you make sure that it will happen? Do you understand? So what do I mean by this? In the initial step, you just train a classifier because you are uniformly sampling. In the next subsequent steps, when WM changes, what do I mean when I say that you will have to train a classifier that would respect this distribution on data samples? There are multiple ways to do this. Okay, one way to do it is when you sample data with replacement, use this distribution on data instead of uniform distribution. That's one way to do it. You understand? So we are assuming that we know how to sample from a sample according to a distribution. So if it's uniform sampling, you just with probability 1 over n you pick a sample, or 1 minus n you don't pick a sample. If the weight is something else, then with probability that particular weight you pick the sample, ith sample, and 1 minus that you pick. Every sample will have a different probability of being picked or unpicked. Okay, when you sample a data set, you sample according to that distribution and then train a classifier. That's how you do it. That's one way to do it. The other way to do it is, let's say that you do a uniform sampling of data. Then, and suppose you are building the constituent classifiers are decision trees. Okay, in decision trees, if you are using the losses like cross entropy or entropy or Gini index, both of them need an estimate of pk, remember, where pk is the number of pk is the probability of a particular class when you do that split. Okay. Now estimate that pk based on the current weights that you are assigning on the data points. Does it make sense? So what was the estimate on pk that we were considering in the naive formulation? It was simply the ML estimate, where you just count the number of data points corresponding to that class and divide it by the total number of data points. But now you don't use uniform distribution, but use these weights to estimate those pk's, and then define the Gini index or whatever metric that you are using for splitting, and then build a tree. That is what is meant by train a weak learner, okay, with the current weights on data wi, or rather I can actually say it this way. Train a weak learner respecting the current weights on data. right. How do you ensure that the classifier respects the current distribution on data? I gave you 2 examples how to do that. See, one easiest way is to sample the data in accordance with WIM. Do you all see that these WIs specify a distribution on data? Not on X, it specifies a distribution on sampling the data, isn't it? If there are 100 points, initially we started by 1 by 100, the probability of picking a point is 1 by 100. After we get this, it is not 1 by 100, right, it is this. If you normalize this, it is a discrete distribution, okay, which will give you the probability of the ith point being picked or unpicked. Make sense? Yeah. So, we will have to train a classifier that way, and then we will have to, the next step is estimate the weighted error. Let us call that epsilon m as what is this? This is simply the weighted count of how many points were misclassified under the current classifier, correct. So, this is the indicator function, okay. If you take this, it is simply counting the number of points on which the current classifier misclassified divided by the total number of points. This would be n. If all weights are 1, then this would be, sorry, all weights are 1 by n, this entire thing would be the count divided by n, okay. So, otherwise it is just the weighted error of misclassification, we do this, okay. Then step is to calculate, estimate the optimal step size . Alpha m as so right now all these are just formulae, we will derive all of them one by one. Just first I will write the algorithm and then, so we estimate alpha m. What is alpha m? It is the optimal weight that is that we have to associate with the classifier, so that we add to the next one, correct. And then we have to update the weights. So, this is the iterative update. So, Wi m plus 1 is Wi m e power minus alpha m yi h m x I. This is the update formula. The next set of weights will be equal to this, okay. And then you have find the ensemble as h m of x to be this is the update that we have. So, this is end for, okay. So, this is what we do in AdaBoost. So, what is being done, let me just quickly run through the algorithm. So, we start with assigning, okay. So, as an overview, what is happening is that every time you are learning a classifier on some weighted data samples. We are doing sampling with replacement, and when we do sampling with replacement, we are assigning weights for individual data points and then using those weights to train a classifier. Okay, and every iteration we update those weights and we iterate over this. This is the overview of the algorithm. Now, how do we get those iterative weights is the question. We start uniformly, okay, and then there is the weighted error that we compute, and with that weighted error we compute what is called as the optimal step size, okay, and using the optimal step size we get the next set of weights which we have to use for the next sampling, and then using those weights we train the current weak learner and we keep iterating over this. This is what the AdaBoost algorithm is, okay. Any questions on the algorithmic procedures? How is it being done? What we will do right now in the next, the coming section is that we will derive all these formulas and show that this is actually a special case of gradient boosting with particular type of loss functions and so on. We will show that. But any questions on the procedure? If you have any questions on procedure.
What are we doing with the next set of weights?
Resample, no? Once you get the next set of weights, train another weak learner respecting the current weights on data. Use those weights, resample and train it again.
So these weights kind of decide the probability of picking up that
particular data set, yes, yeah.
So here the weights are slowly decaying to zero then, at this point.
Why would they?
Because I think the update step you're multiplying with the exponential.
So
are they slowly shrinking to zero?
No, they don't have to, because not all weights will shrink to 0, right. So look at this epsilon m is only data points that are misclassified. So therefore it need not go to 0 at all. So because every weak learner will have some set of points that are misclassified and you are normalizing them as well. The weights surely are changing every time. So in fact we will see that this distribution will try to minimize the error, okay, that the previous classifier made. So that is how it will come out to be, yeah. Procedure wise it's okay, I suppose, yeah.
Since we are sampling different set of points, even though with replacement for each weak learner, how these weights apply to the next by indices?
You still have the, so see, you associate weights with each of the data point. So you associate weights and then sample, no, you will still have the exact same thing coming out, yeah. So only the weights would change. Okay, so now let us look at this algorithm as a gradient boosting. Huh?
Capital N, is it the number of data sets?
Yeah, number of weak learners that you would take. Capital B, whatever we were using B in the previous class, that's, I think we can use B also. Okay, let it be capital M because it is M. The number of ensembles that we use. Exactly. We will ensure that it will happen that way, because that is what I said, when you normalize you will ensure that it sums to 1.
Yeah, but in the formula it's redundant to write summation W for error.
In the formula?
For error.
weighted error.
It's redundant to write.
Of course, yeah. I agree. Yeah. Okay, so now let us look at AdaBoost as gradient boosting. So recall that in gradient boosting what we do is that we write hm of x as hm minus 1 of x plus alpha m times hm. So this is our iterative updates, and we have alpha m and hm, we want these to be the minimizers of the loss that we calculate between yi and hm of x. So, this optimization is over alpha and h. Now, we need to find an alpha and alpha m and an h such that this is optimized, right. That's our goal in gradient boosting. Okay. Now, for AdaBoost, the loss function that is used is as follows. We define L of y comma h of x to be equal to e power minus y into h of x. So, this is called the exponential loss. So, if you remember the definition of loss function that we had, so it should take inputs as the cross product of y and h of x. It will give you, it should give you a non-negative real number. Okay, is it doing it? So, this thing is taking y and h of x as inputs. Okay, and if you multiply, because it is within the exponentiation, it is always non-negative. Okay, and if these two match, if y and h of x match, and remember that in our definition y can take value minus 1 and 1. If y is minus 1 and h of x is also minus 1, this would be loss is lesser, no, because there is a minus here, right. If these two match, then you have lower loss. If these two do not match, then you have higher loss. So, this is a valid loss function. Okay. Now, this implies that the objective that we would want to optimize now will be e power yi into, okay, maybe I will write one more step, have e power minus yi into hm minus 1 xi plus alpha h of xi. It's correct, right? This is the loss function. So, this is what I have written here. All of you with me? Loss with respect to y and hm. So, hm is given by this.
Like the previous equation loss function. Capital H.
Where?
Second.
The loss function shouldn't it be hm minus 1? Yes, we are finding alpha m and hm.
Here.
Because we find hm after finding alpha m and hm.
No. The optimization is over alpha and h, right?
Yeah.
So, you want to find an alpha and h such that the loss on hm is optimized, minimized.
But we find it with respect to the previous hypothesis.
Hm is what you have, I mean, assuming that you know hm minus 1, the optimization is over alpha and h, that is it.
Inside the loss function, shouldn't it be hm minus 1? Because that we haven't yet found, right?
No, this entire thing have to be a function of alpha and h that you optimize over, because you are optimizing over h and alpha, right. So, that has to be a function of h and alpha, and what you evaluate is hm minus 1. That is why we did gradient boosting also, right. Makes sense, right. So, look at this, right. So, this hm minus 1 is something that we know, we are optimizing over alpha and h. That is why it should be, this is saying that you find h and alpha such that the loss on hm of x is minimized, because the choice that you have is on alpha and h. Okay. So, this is what the loss function right now is. So, let us write that down as, so we want to find an h, the h star and alpha star that would minimize this thing. So, we will split the exponentiation now. This is equal to e power minus yi hm minus 1 xi times e power yi into alpha times h of xi. Is all right. So, what did we do? I just split exponentiations into product. Now, we had e power a plus b, I wrote that as e power a times e power b. Okay. This is what we need to optimize now. Now, consider this term e power minus yi times hm minus 1 into xi into e power yi alpha h of xi. See, this term is independent of h and alpha. The optimization variables are h and alpha. So, since this term is independent of that, we can take that as a constant and push it out. Okay. We do not have to. So, let us call this as, define this as wi of m. Okay. So, define that as wi of m. So, this will become correct. Oh, the minus has to come inside, you are saying. So, there is a minus here, yeah, and there is a minus here as well. Correct, yeah. Okay. Now, this is one thing. The other thing is, or maybe before this, we can. There is a side note. Okay, so note WIM is recursive. That is WIM plus 1. What is this equal to? E power minus yi times hm of xi, correct? Now, since hm xi is recursive, this is also become recursive, right? So, what is this equal to? Is equal to e power minus yi times hm minus 1 into x plus alpha n times hm of x, right, xi, yeah. So, this is equal to e power times e power minus alpha m yi hm of x. What is the first term here? This is WIM times e power minus alpha m yi hm of x. This is exactly what we had here, no? See this? So, we recovered this particular update. So, weight update comes from the definition of it, all right. Let us continue. Now, the loss function is this is the term now, right? I just wrote where are we coming from. So, here since we defined this term as WIM, therefore, the loss term will now be equal to WIM e power minus yi alpha times h, and we need to optimize this with respect to h and alpha, correct? This is what we have. Now, here what we can do is as follows, right? So, this is equal to, this term is equal to so I can split this sum into two, right? One, all i's such that yi is equal to h of xi, and all those indices where there is a misclassification, okay? And whenever there is a correct classification, what would this term would be? This term would be WIM, because yi, the product of yi and h of xi will be 1. So, there will be an e power minus alpha term, and this term, whenever there is a misclassification, this term would be e power alpha times WIM, correct? Okay. Now, what we should do is that we should find, so we have to optimize this with respect to h, okay. What choice of h would minimize this? See, what do we have to do? We need to minimize this, right, with respect to h and alpha. Those are the only two variables that we have. We will see how to do it with respect to alpha, but we need to optimize with respect to h as well. So, now tell me what sort of a classifier would minimize this? Come again? Second term is minimized, right? How do you minimize the second term? Second term is the weighted misclassification error, no? Right? So, you will have to ensure that the classifier that you train has to be in such a way that the error on the weighted samples is minimized. That is why I told you, right, you will have to sample according to WIM and then train a classifier in accordance with this. Or if you are looking at trees, you will have to define your loss functions for splitting in accordance with WIM. Do you see what I am saying? So, we will write that the above will be minimized by an h that would minimize the weighted misclassification error, sum of weights on the misclassified points. Correct? We will have to find a classifier, okay, such that the sum of weights of the misclassified points is minimized. So, how do you do this? One way to do it is by sampling, the other way is to tweak the loss function using WIs. Okay. So, what step did it recover in the algorithm? What step did it recover? We will have to recover each step of the algorithm by from this gradient boosting, right? Which step did it recover now? No, the first one, you train a weak learner respecting the current weights, because we are optimizing over h, right? So, it recovered the first step. So, we will have to train when you are doing AdaBoost, you will have to train a classifier finally at each step, right? So, how do you train that classifier? You train it in such a way that the weighted sum of the weights that we are assigning on the data points are misclassified or is minimized. it is recovering the first step. So, now there is only one thing that remains now, which is getting this optimal estimate of alpha. Okay, we will do that now. To get optimal alpha, say this weight term is actually getting overloaded. There is one weight on the data samples, there is one weight on classifiers and so on. So, yeah, just be careful. So, we will have to get this optimal alpha. So, let us do that. Let W, capital W, be equal to the sum of all the weights on data points. So, you take, see, by the way, this is still not normalized. So, if you normalize it, it will become 1. If you divide that, you just made a statement, right, that becomes redundant. That becomes redundant only if you normalize them to make it a distribution. Generally, normalization, you can make it a part of the algorithm, or you do it outside the algorithm as well when you are sampling. For now, we have not normalized it anywhere, right. It is simply a positive real number. Therefore, this W is not 1. Okay. So, let this be this. So, now by definition, we have epsilon m to be equal to 1 by W. So, this is the wherever y is not equal to h of x. So, you recall the definition of this epsilon m, right? Where was this? Yeah, so we defined it as the percentage of the weights, okay, over the samples that are misclassified, right. Epsilon m is, so instead of writing an indicator function here, I wrote this in the summation here. Do you see both of them are same? Okay, I will write it that way. This is equal to, how did we write that? So, I is 1 through n, Wim is an indicator where these two do not match, divided by, this is how we defined it, right? Exactly the same, right? Yeah, instead of you either put it in the summation or you put it as an indicator function summing over everything, same thing. Okay, fine. Therefore, this term is equal to capital W times epsilon m, right, and this term is equal to W times 1 minus epsilon m. Do you see why? Pretty obvious, no? You take this term, you multiply it here, you get this. If you take the sum over all the correctly classified points, you just get it as W times 1 minus epsilon, that is it. Okay. Why did we write it this way? It is because this is our loss function, remember, and we have to basically differentiate this and differentiate this with respect to alpha. H is already done. We already looked at h, right? We will have to do it with respect to alpha and put it to 0, and therefore we are trying to write this term as a function of alpha and epsilon. So, this was the last function, right. So, consider we will stop here and continue in the next lecture.